Hi, Intro to Calc. So before we move on to the next section, we have to build an idea first. So I'm showing you this graph, this blue shaded region, and we've spent a lot of time talking about the area under this curve and the net area and the total area. And so that idea we're going to keep going with today. And because this is so curvy, we're going to take some time to estimate that area. So one of the things to notice is that your scale is going up by 1, which means this input right here is 1. And this is -50, and then this is 1.5. So this is like really a half distance. And that means the area of one of those little squares is 25. And in the context of the problem, it ends up being 25,000 employees. So every single one of these squares is 25. So if we were to ballpark how much area would be just right here, you would count 25, 50, 75, 100, 125, and then maybe these together would all add up to 160. So what I've done over here is I've done all of that work for us already. The signed area represents the areas in each of these little sections. So just like in this section, and then I move on to the next section and the next section, etc. So those are what we call signed areas because it's like positive or it's negative. And then the next thing is really the most important part, and it's how the area accumulates. So as we keep increasing the interval, as that interval gets bigger and bigger, what happens to the change in area, that blue region, if you were just to keep adding? So I found all of those values, and then I graphed it. And so this graph right here is just plotting this interval with that area and this interval with that area, etc. That by the end of that interval, that area was achieved. And what's really cool to see is that right here, we have a minimum. And right here, we have a maximum. And if you look back at this graph is changing from minus to plus, and this graph is changing from plus to minus. So these places are really, really special. This right here represents the derivative of this accumulation function that we made over here on the right-hand side. And that's an interesting idea because this function is f of t, which doesn't sound like a derivative, but because it's a rate, it's 1,000 employees per year, it is a derivative of something larger. I want to show you that idea one more time. So we're going to look at this example right here. So again, in number 2, I looked at the signed areas first, and then I accumulated them. So in this table right here, you'll see how the areas keep adding up. And then looking over here at the graph is a visual display of that table. So here's a minimum, here's a maximum, and here's another minimum. And just as you see over here, this graph is changing from minus to plus, and then from plus to minus, and from minus to plus. So just like in our class, this represents a derivative of the accumulation function that's over here on the right-hand side. That accumulation function has a special name, and we call it the antiderivative. So it's going to be important to be able to go take derivatives, and it's also going to be important to go backwards and find antiderivatives. So we're just going to look at patterns first. So if I have given you a whole bunch of functions, like in our class, then the first thing that we spent doing was finding derivatives. So the derivative of 3x minus 7 is 3. The derivative of x squared is 2x. The derivative of 47x is 47. 1/2 x squared has a derivative of x. That 2 comes down, multiplied by 1/2, reduce the exponent. The same thing happens here. So this derivative is x squared. So compare those relationships between the function and then its derivative. And now when we go backwards, so 5, we say 5 has an antiderivative of f. And so that is going to be 5x. 2x has an antiderivative of x squared. So one of the ways to think about it is what function did it come from so that its derivative would be 2x. For the next one, if it's x, that comes from 1/2 x squared. The 3x squared comes from x. And the x squared function comes from 1/3 x cubed. This should be a cubed. So one thing to know is that if you took the derivative of all of these, you should get right back over here, just by the same rules that we've used in our class this year. And then another important idea is that every single one of these will need a plus c. And a plus c represents some number. It could be 7, it could be 83, it could be negative 45.7. And it's because we don't know if it's there or if it's not there, because the derivative of a constant is 0. So when you see the derivative right here, we don't know if there's more to the original function or not. So it's going to be important to have a plus c. All right, let's make a new column, and let's just keep going with this idea. So capital F represents the antiderivative of little f. That's sort of the general phrase. So like g, big G, would be an antiderivative of little g, which is an antiderivative of g prime. Or you could take derivatives in the forward direction, and you can find antiderivatives in the backward direction. So just for the first few right here, we're going to come up with the antiderivative. So 3x minus 7 will have an antiderivative of this. The minus 7 is easier because this is just a slope of negative 7, which means that it had to come from a line, so negative 7x. The 3/2 is important because there is no fraction in its derivative. That means it had to be eliminated. So 2 times 1/2 does go away, and then you reduce that exponent by 1. X squared has an antiderivative of x cubed times 1/3 plus c. 47x has an antiderivative of 47x squared times 1/2. There again is that idea that the 1/2 and the 2 have to eliminate. 1/2 x squared has antiderivative 1/2 times 1/3 x cubed, because the 3's multiply, and then divide by the 3, and that gets you the 1/2 x squared. And then the last one is 1/3 x cubed, has antiderivative, forgot plus c's in all of these, is 1/3 times 1/4 x to the 4 plus c. So maybe you've realized a pattern, and it's good to realize a pattern with this. So if f equals x to the n, so some power, and that power could be a power of 4, it could be a power of 1/2 or negative 5/6, we say it has antiderivative capital F x to the n plus 1 over n plus 1. And if you just pause the video if you want and look back at the problems we've already done, that totally makes sense. We added 1 to every single exponent, and we also had to divide by that exact same number because we saw that it canceled out later. Remember that the connection between the antiderivative is that accumulation function that we briefly discussed at the very beginning. So it's a really cool connection with integrals, that the antiderivative really does equate to an integral. So number 2, find f, the antiderivative of little f equals 4x squared plus 5x minus 2. So when you're finding the antiderivative of something that's adding and subtracting, you're allowed to just find the antiderivative of each and then string them together. So this will come from 4x cubed over 3 plus 5x squared over 2 minus 2x, and throw on that plus c. All I'm doing is using the rule that we just established, that the exponent has to add 1, and you also have to divide by that exact same number. Number 3. 3x 100 over 100 minus 14x to the 82 over 82 plus c. Number 4. There's that idea again. It's not said in the same language, but this integral is the antiderivative. So 5x squared comes from 5x cubed over 3 minus 3x squared over 2 plus 7x plus c. It represents that accumulation function that we said at the very beginning does represent the antiderivative of whatever's on the inside. Number 5, find the antiderivative. This one's a little bit more challenging because you have a negative exponent and you also have a 1/2 power. So you still apply the formula the same way. Negative 3 plus 1 is negative 2, and then you divide by negative 2. Plus 2x to the 3/2 divided by 3/2 plus c. You can leave it like that, or remember that when you divide by a fraction, it's the same thing as multiplying by the reciprocal. I'm going to take a second on number 6, and I'm going to rewrite this with exponents that are in my numerator. And now we find antiderivatives. So x to the negative 3 over negative 3 minus 3x to the 1/2 over 1/2 plus x to the 5/4 over 5/4 plus c. Realize that there's a lot of different ways to be able to write these. There you go. Number 7. So this is a constant rate, which means that this comes from a line. This is the same thing as 5x plus c. It's just sometimes we don't know what to do with a constant all the time, but remember it came from some line. Number 8, expand. And now you're ready for antiderivatives. So it's got to be complete power, so just a power on its own, and right now we don't have that. So that's why we expand first. X cubed over 3 plus 17x squared over 2 plus c. And the last one for us is not to expand, but to simplify the division. So this is 4x cubed minus 3 plus 7x to the negative 2 dx. And now you can find antiderivatives of each of these. So this comes from x to the 4 minus 3x plus 7x to the negative 1 over negative 1 plus c. So the major idea for today is that some integral of a derivative is equal to its antiderivative plus c. And that antiderivative, you could write it with a little f. You could also do little f on the inside, and it's equal to its antiderivative, capital F, plus c. You just have to make sure that those look different. And the power formula that we used So I just write that in the very basic sense with the power rule, and then don't forget that you'd have to have a plus c throughout. That's it for 5.4. You've got a quizzes to do now.